Chapter 1 Introduction: The Strange as the Rule of the Universe. Sometimes we believe we know the sky. We look up from our window and see luminous points as if they were all the same. Yet up there, hidden among those familiar lights, exist worlds so utterly bizarre that they defy the very laws of physics as we understand them. There are stars composed entirely of quarks, planets that shine and gleam like colossal diamonds, and black holes that somehow manage to emit sounds into the vacuum of space. Each one seems to have sprung from an impossible dream, and yet science contemplates them all with genuine, wide-eyed astonishment. Now, settle in comfortably, adjust the sound to your liking, and allow the night to slowly unveil the universe's most profound secrets. Welcome to Deep Space Calm, where every story is a bold step toward the ultimate unknown. If you enjoy journeys of this kind, be sure to subscribe and leave your like to continue advancing together into the most extraordinary depths of the cosmos. When you hear the word strange or bizarre, you probably think of something that deviates from the ordinary, something that doesn't fit with what you already know. But out in the universe, the strange is not the exception. It is, quite literally, the rule. Out there, what seems utterly impossible to us occurs every single day. The cosmos simply does not abide by the norms of our terrestrial intuition. It engages with forces that warp the very fabric of space-time, with temperatures capable of instantly pulverizing any known material, and with such extreme densities that a mere handful of that substance could, without effort, crush an entire mountain. On Earth, our common sense of normal is shaped entirely by the gravity we feel, by the air we breathe, and by the warm sunlight that sustains us. Everything we know exists within a narrow and specific range of conditions, neither excessively cold nor unbearably hot, neither overwhelmingly dense nor a total void. But venture beyond this familiar comfort zone, and the rules completely change. And when the fundamental rules change, the true wonders, the real prodigies of the cosmos, begin to appear. For the scientific community, something strange does not inherently mean mysterious or supernatural. Rather, it signifies that its behavior or composition does not conform to what our most precise equations predict. It's a word that sounds almost emotional, but in reality, it is a highly technical term. Astronomers use it with immense respect because every cosmic oddity is a profound crack through which new understanding filters into our knowledge base. Every time the universe showcases a phenomenon that simply doesn't fit the existing models, physics takes a monumental step forward. For centuries, scientists have attempted to categorize cosmic objects in a tidy, orderly fashion, as if the universe could be neatly organized on shelves. Stars, planets, comets, galaxies. Each category is furnished with its precise definition, but every so often something appears that shatters this harmony. An object that, according to established models, should not exist. A light that pulses in an unexpectedly different way. A pattern that refuses to fit into any known type. It is in those moments that the word strange acquires its true scientific weight and excitement. For instance, there are bodies whose density is so incredibly colossal that it defies all common sense. Just imagine a single teaspoon of matter weighing as much as an entire mountain. That's what occurs inside a neutron star. Or visualize temperatures that are simply beyond human conception, places colder than any human-built laboratory, or so blistering hot that matter effectively ceases to be matter in its conventional form. There are alien worlds where molten metals literally rain down, or where the oceans are composed of liquid methane. And far beyond even these extremes, there are zones where reality itself appears to fold in on itself, creating dark portals that actively devour everything that approaches their horizon. The universe is replete with anomalies that force us to constantly redefine our most basic ideas about what is truly possible. Astronomers study them using increasingly precise instruments, telescopes that capture light invisible to the human eye, radio telescopes that listen to the faintest whispers of deep space, and detectors that sense the vibration of a gravitational wave that has traveled millions of years from its violent origin. Each new instrument allows us to observe a little more of the cosmos's hidden countenance, and with every discovery, we come to understand that our cherished notion of normality is extraordinarily localized and provincial. Because while the Earth is our comfortable, familiar home, the universe is a vast, borderless ocean where millions of forms of existence float, none of which adhere to our familiar local laws. What would be considered absurd here is nothing more than everyday occurrence out there. In a distant galaxy, a star might live its life enveloped in magnetic fields powerful enough to instantly detonate any metal. A planet could orbit its sun so closely that one of its years lasts a mere few hours. A black hole, in a sense, can actually sing, literally vibrating the space-time fabric with notes so gravelly deep we couldn't hear them, but we can, and do, precisely measure them. All of this is strange to us, but it is entirely unremarkable to the universe. It knows no concept of weird. It only knows the concept of possible. This is precisely why scientists often state that the cosmos is the most effective and elaborate laboratory imaginable. We don't need to invent grand experiments. We simply need to diligently observe what is already unfolding out there. The inherent difficulty lies in trying to understand it all, and it is right there that the beauty of the scientific mind emerges, transforming pure astonishment into solid knowledge and transforming a deep mystery into a single, well-formulated question. The curious thing is that the more we learn, the more exceptions we encounter. Every new observation expands the comprehensive map of the possible and simultaneously reveals new boundaries and challenges. What once seemed like a one-off oddity rapidly becomes an entire category of objects. Neutron stars, for example, were utterly unknown until little more than half a century ago, and today we know that there are thousands upon thousands of them within our own galaxy. The strange ceases to be strange only once it is thoroughly understood, but the universe is a restless place. The moment we manage to resolve one great mystery, it is already showing us another, even more profound one. This is, perhaps, one of the most beautiful paradoxes of human knowledge. The more we gaze upon the cosmos, the more clearly we understand how little we truly comprehend. The inherent strangeness is not just out there, but also right here, within us, in our deeply ingrained insistence on finding sense and meaning in a universe that has absolutely no obligation to provide it. And yet, we continue to observe. We continue to ask questions, because ultimately, every strange object we uncover out there is a magnificent reflection of our own persistent curiosity right here within. The universe does not only challenge our fundamental logic with its sheer scale, it also does so with its history. We know it originated approximately 13.8 billion years ago in an event called the Big Bang. But what came before that, if such a before even existed, remains an absolute mystery. We know that space is rapidly expanding, carrying galaxies farther and farther away from each other, but we do not know precisely why that expansion is accelerating. We know that the vast majority of the universe is made up of matter and energy that we cannot see or touch, dark matter and dark energy, but we still have no idea what they truly are. And in the midst of this incomprehensible vastness, objects that appear to be sprung from the wildest imagination suddenly manifest. Some radiate with the intense luminosity of 1,000 suns. Others are so intensely dark that not even light can escape their gravitational grasp. Some rotate so incredibly fast that they defy the accepted laws of mechanics. Others remain virtually motionless, yet emit waves that subtly distort the very texture of space itself. Every single one of these phenomena has its rightful place in the cosmic tapestry, and although they may seem isolated or unconnected, they are all ultimately bound together by the very same fundamental forces: gravity, electromagnetism, and the nuclear interactions. These are the same laws that govern the motion of a single leaf falling from a tree or the steady rhythm of your heartbeat. It's just that out there, those laws operate at extremes that we will simply never fully experience here. So tonight, as you get comfortable and your breathing slows, we are going to let our minds travel far beyond the familiar sky. We will begin by exploring one of the most fascinating and intensely dense oddities of the cosmos, the neutron stars, places where matter is so utterly compressed that it behaves as if reality itself were buckling under its own immense weight. A powerful reminder that even the silent universe can conceal the most intense secrets within the smallest, most compact forms. Prepare to discover how an object the size of an average city can possess more mass than our entire sun, and how its surface is so incredibly hard that it makes steel feel like cotton. Prepare to understand why some of these stellar corpses spin hundreds of times per second, emitting regular pulses of light that sweep across the cosmos like enormous, distant cosmic lighthouses. And finally, prepare to be astonished by the realization that all of this extreme density might only be the beginning of something even stranger and more profound. Chapter 2. Neutron stars, the densest matter. Imagine holding a simple teaspoon in your hands. Now try to picture that exact teaspoon weighing several million tons. Not millions of grams, not even millions of kilograms. We are talking about millions of tons. Its colossal weight would be enough to immediately sink, piercing through the floor, effortlessly drilling through the entire Earth, and emerging out the other side. This is the staggering level of density of the matter found in a neutron star, one of the most utterly strange and extreme objects known throughout the entire observable universe. These stars are born from the violent, cataclysmic death of other, much larger stars. When a massive star finally exhausts its nuclear fuel, the hydrogen and helium that powered it, it can no longer generate the outward pressure needed to resist the inward pull of its own immense gravity. Its core collapses inward with a force so brutal and unstoppable that the existing protons and electrons are violently squeezed together, essentially fusing into pure neutrons. In that terrifying instant, the star's heart is compacted, forming a tiny sphere scarcely 20 kilometers, about 12 miles, in diameter, yet containing a mass greater than that of our Sun. The remainder of the star explodes outward in a spectacular supernova, a cosmic flare so incandescently bright that for a few days it can momentarily outshine its entire host galaxy. And what remains at the very center, that relentlessly collapsed core, is this cosmic relic, the incredible neutron star. If you could somehow get close to one of these celestial objects, though naturally you would not survive even a fraction of a second, you would see something completely unlike any common star. It is not a glowing, luminous sphere of fire, but rather an incredibly small, compact, and dark object, wrapped in an unbelievably powerful magnetic field. Its crust is extraordinarily hard, almost like solid steel, yet existing at a temperature exceeding 1,000,000 degrees Celsius. It is so compact that its immense gravity significantly bends and warps the very light it emits, distorting the space surrounding it. The result is a celestial body that seems to aggressively challenge all established physical logic. The density of a neutron star is so utterly extreme that a fragment the size of a simple sugar cube would weigh as much as all of humanity combined. To grasp this astonishing concept, consider that the total mass of our entire Sun, compressed and squeezed down to the size of an average, medium-sized city like Manhattan, would be comparable to the density of these unbelievable objects. On Earth, even the densest materials we know, such as osmium or iridium, seem ridiculously spongy in comparison. Inside a neutron star, matter is packed so tightly that atoms have entirely ceased to exist as discrete entities. The electrons and protons have merged into neutrons, and these neutrons are packed so densely together that they are practically touching each other in a continuous quantum soup. This extreme compression endows neutron stars with utterly unique properties. Their surface gravity is approximately 200 billion times stronger than that of Earth. If you could, theoretically, walk on one, which is, of course, physically impossible, your weight would be so colossal and instantaneously overwhelming that you would be crushed immediately, reduced to a wafer-thin layer of atoms. An object dropped from just 1 meter above its surface would impact with the devastating energy equivalent to a small nuclear bomb. The very space-time around it is so severely distorted that the light it emits curves, allowing observers like us to see parts of its surface that, from our perspective, should actually be hidden behind the star's horizon. This effect is a profound illustration of Einstein's general relativity at its most extreme. But sheer density is far from the only astonishing characteristic of these stars. Many of them also spin on their axis at absolutely dizzying speeds. Some complete a full rotation in mere milliseconds, essentially rotating hundreds of times every single second. Imagine an object the size of a major metropolis, containing more mass than the Sun, spinning faster than the blades of a high-powered kitchen blender. This frantic rotation is an inherent vestige of the original star. When the core collapses, it conserves its angular momentum, but as its size dramatically shrinks, the rotational velocity proportionally skyrockets, much like a figure skater spinning faster when they pull their arms inward. Furthermore, these stellar remnants possess incredibly potent magnetic fields. In some documented cases, these fields are trillions of times more intense than that of the Earth. These ultra-powerful magnetic fields actively interact with charged particles surrounding the star, accelerating them to velocities nearing the speed of light and generating focused jets of electromagnetic radiation that are violently fired out from the star's magnetic poles. If those focused beams happen to sweep across and point toward Earth, we detect them as regular, precise pulses of light or radio waves. This phenomenon is why many neutron stars are specifically termed pulsars, cosmic lighthouses that flash with a stunning, almost perfect clockwork precision. The landmark discovery of pulsars in 1967 was one of the most exciting and fascinating moments in modern astronomy. Astrophysicist Jocelyn Bell Burnell detected radio signals arriving with such astonishing regularity that it was initially speculated they might be structured messages from an extraterrestrial civilization. They were even playfully nicknamed LGM, short for Little Green Men. However, It was soon correctly understood that these perfectly regular signals originated from rapidly rotating neutron stars, whose focused beams of radiation swept across space just like a lighthouse turning on the coastline. This crucial discovery confirmed the long-held theoretical predictions about the existence of these extreme objects, and immediately opened a completely new and vital window for studying the universe's most esoteric states. Pulsars are not only fascinating due to their extreme physical nature, but also due to their significant scientific utility. Because they spin with extraordinary, predictable regularity, some pulsars are actually as precise as the very best atomic clocks here on Earth. Astronomers use them as natural galactic beacons to meticulously study the properties of space-time itself, to effectively detect the subtle presence of gravitational waves, and to accurately map the distribution of matter within our own galaxy. In a very real sense, pulsars are invaluable natural tools gifted to us by the universe to explore its deepest, most fundamental secrets. Deep inside a neutron star, the conditions are even more extreme and challenging to model. The pressure at its core is so intensely high that even theoretical physicists are not entirely sure what definitive form the matter takes there. It is widely hypothesized that in the innermost layers, exotic states of matter may exist that we have never been able to successfully reproduce in any laboratory environment. Some sophisticated models suggest that the neutrons themselves might actually decompose into their fundamental constituents, the quarks, creating what is dramatically referred to as quark matter. If this prediction is confirmed as true, then in the hearts of these stars, we could potentially be observing matter in its most basic form, exactly as it existed only fractions of a second after the Big Bang. Neutron stars can also exist in binary systems, orbiting alongside another star or even another neutron star. In these spectacular cases, the combined gravity of both objects can so severely distort space-time that it generates powerful gravitational waves, ripples in the very fabric of space that travel outward at the speed of light. When two neutron stars finally collide in a colossal cosmic embrace, the event, called a kilonova, releases such an unbelievable, gargantuan amount of energy that it can be detected from billions of light-years away. These catastrophic collisions not only produce powerful gravitational waves, but also synthesize and generate heavy chemical elements like gold and platinum. In a profound literal sense, the gold in your ring or your watch likely originated from the catastrophic merging of two neutron stars in some remote, violent corner of the universe, billions of years ago. These incredible stars also serve as a crucial reminder of something fundamental. The universe is neither static nor gentle. It is inherently violent, dynamic, and perpetually filled with powerful processes that constantly transform matter and energy. Neutron stars are essentially stellar corpses, but they are far from dead in the conventional sense. They remain profoundly active, constantly emitting radiation, spinning at impossible velocities, and powerfully deforming the space around them. They are silent, yet potent, witnesses to the cycle of cosmic death and rebirth, living reminders that even in the most absolute and violent destruction, the universe always finds ways to create something new, something strange, and something utterly unique. And yet, as extreme and mind-boggling as neutron stars are, they are not the densest nor the strangest objects the universe has to offer. Others exist that are even more profoundly bewildering and challenging to our understanding, as we will explore in the next chapter. Chapter 3: Quark Stars and Magnetars, Magnetic Extremes. If neutron stars already appear to represent the absolute limit of what is physically possible, the universe invariably shows us that it can still push the boundaries much further. There exist theoretical objects called quark stars, whose density is speculated to surpass even that of neutron stars. And there are also the well-confirmed magnetars, which are a specific type of neutron star possessing magnetic fields so incredibly intense that they could literally rip the atoms right out of your body, even if you approached within thousands of miles of them. Both represent the absolute extremes of matter and energy, locations where the fundamental laws of physics are stretched and tested to their breaking point. Let's begin our exploration with quark stars. To properly understand their nature, we must first recall that neutrons themselves are not fundamental particles. They are composite particles, composed of smaller entities called quarks, which are held together by the strong nuclear force, one of the four fundamental forces of the universe. Under normal, everyday conditions, quarks never exist in isolation. They are always firmly confined within protons, neutrons, or other subatomic particles. But deep within the core of a neutron star, where the pressure is unimaginably high, something extraordinary might occur. The pressure could potentially be so extreme that the neutrons violently disintegrate, unleashing and liberating the quarks that comprise them. Should this dramatic event take place, the result would be a quark star, an object theoretically even denser than a neutron star, composed of free quarks floating in a turbulent sea of pure energy. This exotic state, known as quark matter, is so rare and unusual that it has never been directly observed in nature, except perhaps during the very first fractions of a second after the Big Bang, when the entire universe was a blazing hot plasma of quarks and gluons. Recreating those specific conditions here on Earth is nearly impossible, although some sophisticated experiments in particle accelerators have managed to briefly produce similar, fleeting states of matter. The ultimate existence of quark stars remains largely speculative. We do not know with absolute certainty if they truly exist, primarily because, from vast distances, they would be virtually indistinguishable from normal neutron stars. They would likely emit similar radiation, possess comparable masses, and rotate in much the same manner. However, their internal structure would be radically different. Whereas in a neutron star, the neutrons largely maintain some identity as particles, in a quark star, that entire subatomic structure would have dissolved, leaving behind only quarks in a state of freedom that decisively challenges our habitual understanding of matter. Some theoretical models propose that quark stars might possess a crystalline surface, an unbelievably hard crust, formed by quarks organized into perfect geometric patterns. Other models suggest they might be entirely fluid, lacking any clear, distinct boundary between the core and the exterior. What we do know is that if they do exist, they would compress significantly more mass into the same volume, making them even denser than neutron stars. A fragment of quark matter the size of a tennis ball could theoretically weigh as much as the entire moon. Yet, even without definitively confirming the existence of quark stars, we already know of objects that are extreme enough to thoroughly challenge the human imagination: the magnetars. These are a special and terrifying class of neutron star that possess the most intensely powerful magnetic field currently known in the universe. To place this magnitude in perspective, the Earth's magnetic field registers at approximately half a Gauss. A common refrigerator magnet registers about 100 Gauss. A medical MRI machine utilizes fields up to 30,000 Gauss. But a magnetar can possess a magnetic field reaching a mind-boggling 1,000 trillion Gauss, a quadrillion Gauss. It is a number so completely astronomical that it becomes genuinely difficult to visualize or comprehend its sheer power. What exactly does it mean to possess a magnetic field of such immense power? It means that the very space surrounding the magnetar is dramatically deformed. The magnetic field lines are so intensely concentrated that they actively affect the behavior of atoms, mercilessly stretching and twisting them. If you could somehow approach a magnetar from a distance of just 1,000 kilometers, which would obviously be instantly fatal, its magnetic field would immediately begin to interfere with the delicate chemical bonds of your body. The atoms that form your cells would physically elongate, following the invisible magnetic lines of force, literally disintegrating your matter at a molecular level. Furthermore, the magnetic fields of magnetars generate colossal electrical currents both on their surface and in the space surrounding them. These currents superheat the magnetar's crust to extreme temperatures, causing it to emit powerful bursts of X-rays and gamma rays, which are the most energetic forms of electromagnetic radiation. Occasionally, the magnetar's incredibly solid crust cracks due to the immense magnetic tension, instantly releasing more energy in a single moment than our sun emits over thousands of years. These tremendous events, known as gamma ray bursts, are so devastatingly bright that they can be reliably detected from the far reaches of the observable universe. On December 27, 2004, astronomers successfully detected one of the most intense gamma ray bursts ever recorded. It originated from a magnetar designated SGR 1806-20, located approximately 50,000 light-years away from us. For a fleeting tenth of a second, that magnetar released more total energy than our sun will generate over the next 100,000 years. The resultant radiation was so intense that, despite the vast distance, it significantly perturbed the Earth's ionosphere, dramatically affecting radio communications across the entire planet. Had that same magnetar been located only 10 light-years from us, the blast would have been powerful enough to potentially extinguish a large portion of life on Earth. Magnetars are exceedingly rare. It is estimated that in our galaxy, the Milky Way, only a few dozen of them exist, compared to the thousands of regular neutron stars. We do not know precisely why some stellar cores collapse to form magnetars, while others become ordinary pulsars. One prominent hypothesis suggests the difference is related to the original star's rotational speed. If it spun extremely fast prior to collapse, it might have generated a powerful dynamo effect that amplified its magnetic field to extreme trillion Gauss levels. Another theory proposes that certain types of supernovas, which are far more energetic than the usual ones, create the necessary initial conditions for a magnetar to form. What is truly fascinating about these bizarre objects is that they compel us to profoundly rethink what we believe we know about magnetism. Here on Earth, magnetic fields are useful but relatively weak. We employ them in compasses, electric motors, and hard drives. But within a magnetar, magnetism transforms into the dominant force, capable of shaping matter and space with the same overwhelming authority as gravity. It serves as a vital reminder that the fundamental forces of the universe do not adhere to fixed hierarchies. Under the exact right conditions, any one of them can ultimately become supreme. Magnetars also pose deep and challenging questions about the very nature of matter under these extreme conditions. What happens to atoms when they are subjected to such intensely powerful magnetic fields? How do electrons behave when the magnetism is so strong that it profoundly deforms their quantum orbits? Is it possible that within the internal structure of a magnetar there exist entirely unknown phases of matter, states that we may never be able to reproduce in a laboratory because they require unreachable energies and pressures? These complex questions do not yet have definitive answers, but they are precisely the type of challenging inquiries that propel science forward. Every neutron star, every magnetar, and every potential quark star serves as a natural, cosmic laboratory where the universe executes experiments that we could never hope to design ourselves. And by meticulously observing them, by measuring their radiation, their rotation, and their magnetic fields, we are steadily learning about the deeper, more profound laws that fundamentally govern all of reality. So, as you sink further into rest and your mind begins to relax, consider this incredible fact. Far out there, in some remote corner of the galaxy, there are stars made of the densest matter imaginable, spinning at unbelievable speeds, and enveloped in magnetic fields that would twist and distort space itself. And even though they are thousands of light years away, their mere existence tells us something vital about the universe. That even in the most physically extreme places, the laws of physics continue to function, adapt, and reveal new, astonishing facets of reality that we never could have conceived. Chapter 4: Impossible Exoplanets, Worlds of Diamond and Molten Metal. For thousands of years, the only planets we knew of were those within our own solar system. We were familiar with rocky worlds like Earth and Mars, the swirling gas giants like Jupiter and Saturn, and the icy, distant orbs of Uranus and Neptune. This seemed to establish the universal norm: ordered, predictable planets orbiting their central star at reasonable, calculated distances. However, when astronomers began the systematic discovery of planets orbiting other stars, the first confirmed ones appearing in the mid-1990s, the universe immediately demonstrated how absurdly limited our prior vision had been. Exoplanets, those distant worlds circling far-off stars, are so deeply strange and wildly diverse that they defy any simple terrestrial-based classification. Today, we know of thousands of confirmed exoplanets, and each new one often seems more bizarre than the last. There are planets where supersonic winds cause molten glass to rain down horizontally. There are worlds entirely engulfed by deep global oceans, without a single visible island of dry land. There are colossal gas giants that orbit so perilously close to their star that their atmosphere is constantly evaporating away, leaving a trailing plume of gas much like a comet's tail. And there are planets so intensely dense that they might be composed almost entirely of crystallized diamond. Let's begin with one of the most astonishing discoveries: the diamond planets. In 2004, astronomers identified an exoplanet named 55 Cancri E, or Janssen, located approximately 40 light-years from Earth. This world is roughly twice the size of our own planet, but possesses a much greater mass, strongly suggesting that its fundamental composition is radically different. According to theoretical models, 55 Cancri E may be composed primarily of carbon rather than the silicates that make up Earth's bulk. And under the extreme internal conditions of pressure and temperature that reign within its interior, a vast amount of that carbon would have crystallized, forming pure diamond. Imagine an entire planet constructed out of diamond. We are not talking about small, scattered crystals. We are describing a world where the crust, the mantle, and possibly even the core are made up of this crystalline form of carbon. Its surface would be impossibly hard, brilliantly lustrous, and would reflect the light of its parent star with a blinding, dazzling flash. Naturally, you could not simply land there and start mining diamonds. The surface temperature of 55 Cancri E exceeds 2,000 degrees Celsius, over 3,600 degrees Fahrenheit, which is hot enough to instantly melt most known metals. Furthermore, it orbits so incredibly close to its star that 1 year there lasts barely 18 Earth hours. It is an utterly scorching inferno wrapped entirely in diamond crystal. How does such an impossible planet form? The key lies in the chemical composition of the initial cloud of gas and dust from which it originated. In our own solar system, oxygen is far more abundant than carbon, which favors the formation of silicates and oxides, rock and metals. But in other galactic regions, these proportions can be fundamentally reversed. If a star and its attendant planets form in a carbon-rich area, the resulting worlds will have a completely different chemistry. Instead of silicon rocks, they will possess graphite and diamond. Instead of water, they might harbor liquid hydrocarbons like methane or ethane. These are worlds that operate under an alternative chemistry, which is just as valid as our own, but fundamentally alien. Then there are the hot Jupiters, a class of exoplanets that, according to our initial theories of planetary formation, should not exist. They are gas giants the size of Jupiter or larger, yet they orbit extremely close to their stars, at distances where the temperature is so brutally high that even metals vaporize. The first hot Jupiter discovered was 51 Pegasi b, or Dimidium, in 1995, and its existence severely shook the foundations of planetary astronomy. Based on models of the time, gas giants could only form far from their star, where it was cold enough for ice and gas to successfully condense. But here was one, circling its sun in just 4 Earth days, with surface temperatures exceeding 1,000 degrees. The explanation that scientists subsequently developed is quite fascinating. These planets did not form where they currently reside. They were born in the outer, colder regions of their solar systems, much like Jupiter and ours, but then migrated inward. This process of planetary migration occurs due to complex gravitational interactions with the thick disk of gas and dust surrounding young stars, or through gravitational encounters with other planets that drastically alter their orbits. The result is a gas giant now trapped in a blazing hot, close-in orbit, being actively cooked under the fierce heat of its star. The conditions on these hot Jupiters are truly hellish. Their atmospheres are so hot that atoms of iron and other metals float around as vapor. In some cases, these metals condense on the night side of the planet and fall as rain composed of molten iron. Others possess atmospheric winds that roar at speeds of several thousand kilometers per hour, distributing the heat unevenly and creating colossal, centuries-long storms. One particular exoplanet, HD 189733b, possesses a deep blue-colored atmosphere, not due to water, like our oceans, but due to silicate particles that scatter light in a similar way. But this deceptively beautiful blue sky hides an inferno. The temperature exceeds 1,000 degrees, and the winds scream at 7,000 kilometers per hour, carrying razor-sharp crystals of glass that cut like microscopic blades. We also have the ocean planets, worlds completely covered by water in its various exotic forms. Some might feature liquid oceans hundreds of kilometers deep, without any visible rocky bottom. Under these crushing extreme pressures, the water would adopt exotic forms, hot ice that exists in a solid state despite high temperatures due to the colossal pressure, or supercritical water that is neither fully liquid nor fully gaseous, but something uniquely in between. These worlds could possess dense atmospheres of pure water vapor and perpetual clouds, with continuous electrical storms illuminating their dark skies. One of the most intriguing and widespread concepts is that of rogue planets, worlds that orbit no star at all. They were violently ejected from their original solar systems during complex and chaotic gravitational encounters, and now silently wander through interstellar space in complete, profound darkness. Some studies suggest that there could be billions of these orphaned planets throughout our galaxy, possibly even outnumbering the stars themselves, Without a stellar heat source, these worlds are frigid and dark, frozen in an eternal silence. Yet some might retain enough internal heat generated by radioactive decay or residual energy from their formation, potentially allowing for liquid subterranean oceans to exist beneath their icy surfaces, a compelling potential refuge for forms of life adapted to absolute darkness. And then there are the super-Earths and the mini-Neptunes, distinct categories that have no direct equivalents in our solar system. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Some might possess dense hydrogen atmospheres, others could be arid, airless worlds, and a few might perhaps harbor temperate surface conditions with liquid water. Mini-Neptunes are smaller than Neptune but still qualify as gas giants, with thick, expansive atmospheres of hydrogen and helium blanketing rocky or icy cores. The sheer variety is so immense that every new discovery radically expands our working comprehension of what is structurally possible in planetary architecture. The discovery of these strange, impossible worlds teaches us something deeply fundamental. Our solar system is not the universal template. It is merely one specific example within a countless array of possible configurations. Earth, with its breathable atmosphere, temperate oceans, and vibrant biosphere, is a remarkably special case within a much broader, more extreme spectrum. And this realization raises fascinating questions about the prospect of life. If planets can be this incredibly diverse, how diverse might the forms of life inhabiting them be? Could life possibly exist in a subterranean ocean of a rogue planet? Or perhaps in the thick, high clouds of a hot Jupiter, floating on currents of superheated gas? Every single exoplanet discovered is a brand new window into a boundless universe of possibilities. And as you relax this evening, remember that out there, orbiting stars that are barely pinpricks of light in our sky, exist worlds where the rain is made of molten metal, where the oceans might be liquid diamond, and where the sky flashes with relentless storms of glass crystals. These are worlds that aggressively defy our imagination, but which exist, real and tangible, patiently waiting to be fully explored someday. Chapter 5: Black Holes, the Devourers of Space-Time. If there is one object in the universe that truly embodies the concept of the impossible, it is the black hole. It is a region where gravity is so intense that nothing, not even light, can possibly escape its grip. A point in space where time itself grinds to a halt, where the known laws of physics cease to function, and where matter vanishes, swallowed by something we can neither see nor touch. Black holes are the most extreme anomalies in the cosmos, yet they exist by the millions throughout our galaxy, silent, invisible, and patiently waiting. The initial idea of a black hole was conceived long before we possessed the technology to actually detect them. As far back as the 18th century, the English scientist John Michell speculated on the existence of stars so massive that their gravity would prevent light from ever escaping their surface. But it was Albert Einstein, with his groundbreaking theory of general relativity in 1915, who laid the precise mathematical groundwork to truly understand them. Einstein demonstrated that gravity is not a mysterious force that pulls on objects, but rather a profound curvature of space-time caused by mass. The more massive an object is, the more it warps the space surrounding it. And if you compress enough mass into a sufficiently small volume, that curvature becomes effectively infinite. A black hole is formed. Ironically, Einstein himself did not believe that black holes could realistically exist. He found them too extreme, too bizarre and unsettling. But the universe, naturally, does not consult our preferences. In 1971, astronomers detected the first solid evidence of a black hole in a binary system called Cygnus X1. Since then, we have found thousands of them, ranging from stellar mass black holes formed by the collapse of massive stars to the colossal, supermassive black holes that reside in the centers of virtually all large galaxies and contain millions or even billions of times the mass of the Sun. How does a black hole actually form? The process begins with the dramatic death of an extremely massive star, one significantly larger than our Sun. When that star completely exhausts its nuclear fuel, it can no longer support its own crushing weight. Its core violently collapses inward in a fraction of a second, compacting down to a point of theoretical infinite density called a singularity. The star's outer layers simultaneously explode in a powerful supernova, while the core continues its relentless collapse until the gravity becomes so overwhelmingly strong that nothing, not even light, can escape. At that precise moment, a black hole has been formed. Surrounding the singularity is an invisible boundary known as the event horizon. This is the critical point of no return. Anything that crosses this boundary, whether it is matter, light, or any form of information, is irrevocably doomed to fall toward the center and vanish forever. From an external vantage point, the event horizon appears as a perfectly black sphere because it emits or reflects absolutely no light. It is, quite literally, a true hole in the fabric of space-time, a region where reality as we know it ceases to have meaning. But although black holes do not emit light, they are not entirely invisible to us. We can successfully detect them by observing their powerful effect on the surrounding environment. When a black hole is positioned near a companion star, its gravity strips material away from that star, forming a swirling accretion disk, a spiral of gas and dust that rotates at incredibly high velocities before inevitably plunging past the event horizon. This infalling material heats up so intensely from friction that it emits fierce X-rays, allowing us to reliably detect the black hole's presence. Furthermore, its immense gravity distorts the light coming from objects located behind it, creating a powerful effect called gravitational lensing that reveals its location. One of the most unsettling characteristics of black holes is their profound impact on time. According to general relativity, the stronger the local gravity, the slower time passes. Near the event horizon, time slows down so drastically that, from our external perspective, an object falling into a black hole would appear to freeze right at the edge, seemingly stopping forever. But from the perspective of the object that is falling, time proceeds normally. It would cross the horizon without sensing anything unusual at that moment, though shortly thereafter it would be torn apart by the tremendous gravitational tidal forces, a terrifying process known as spaghettification, where the object is stretched into a long, thin strand due to the vast difference in gravity between its nearest and farthest points from the black hole. Black holes also possess a surprising property. They can rotate. When a star collapses, it conserves its angular momentum, so the resulting black hole spins on its axis. Some rotate so rapidly that the very fabric of space-time itself is dragged along in a powerful whirlwind around them, a strange phenomenon called frame dragging, or the lens-thirring effect. Near a rapidly rotating black hole, it is impossible to remain perfectly still. Space itself forcefully drags you in circles, compelling you to move even if you apply no physical force. One of the greatest unresolved mysteries surrounding black holes is what precisely happens at their center, at the singularity. According to the strict equations of general relativity, the density and the curvature of space-time become infinite there, which is considered physically impossible. Infinities in physics typically indicate that our current theory is fundamentally breaking down, that we are in urgent need of a new, more complete description. Most physicists believe that at the center of a black hole, the laws of quantum mechanics must enter into play, but we do not yet have a successful, complete theory of quantum gravity that allows us to accurately describe that region. This remains one of the greatest unsolved problems of modern physics. Then there are the supermassive black holes, gargantuan monsters that dwell at the centers of nearly all large galaxies, including our own. Our galaxy, the Milky Way, has a supermassive black hole at its center called Sagittarius A star, possessing a mass of approximately 4 million times that of the Sun. These stellar giants did not form from the collapse of a single star, but through much more complex processes: mergers of smaller black holes, massive accretion of surrounding gas, or perhaps even primordial seeds that grew steadily over billions of years. In 2019, the Event Horizon Telescope, a worldwide network of radio telescopes working in unison as a single Earth-sized instrument, successfully captured the first direct image of a supermassive black hole at the center of the galaxy M87. The resulting image showed exactly what Einstein's equations had predicted: a brilliant ring of light surrounding a perfect circular shadow. That shadow is the event horizon, the definite boundary beyond which nothing can return. It was a historic moment, the definitive visual confirmation of something that for decades had been purely theory and mathematics. Black holes do not only devour matter, they can also powerfully expel it. When a supermassive black hole accumulates material in its accretion disk, some of that material is ejected in colossal jets that are fired outward from the black hole's poles at velocities approaching the speed of light. These jets can extend for millions of light years, slicing through entire galaxies and injecting enormous amounts of energy into the intergalactic space. These are some of the most energetic and violent phenomena in the universe, capable of profoundly influencing the evolution of the host galaxies that surround them. And finally, there is Hawking radiation, a quantum phenomenon predicted by the physicist Stephen Hawking in 1974. According to Hawking's theory, black holes are not perfectly black. They emit an extremely weak form of thermal radiation due to quantum effects occurring right at the event horizon. This radiation causes black holes to slowly lose mass, effectively evaporating over cosmic timescales. For a stellar mass black hole, the process would take longer than the current age of the universe, but for hypothetical microscopic black holes, the evaporation would be rapid. This revolutionary idea suggested that black holes possess temperature and entropy, thermodynamic properties that connect gravity with quantum physics in ways we still do not fully comprehend. Black holes also introduce the information paradox, one of the most profound enigmas in modern physics. If a black hole eventually evaporates completely through Hawking radiation, what happens to the information about everything that fell into it? According to the laws of quantum mechanics, information cannot be destroyed. However, according to general relativity, anything that falls into a black hole vanishes forever. This contradiction has fueled decades of intense debate and remains an issue that is not yet fully resolved. As you prepare for sleep tonight, think about this. Somewhere in the distant galaxy, there are black holes actively devouring entire stars, mercilessly tearing them apart with their gravity and dragging the remnants into oblivion. There are supermassive monsters at the centers of faraway galaxies, so massive they fold space-time as if it were soft putty. And at the heart of every single one of them, there is a singularity, a point where all our current physical laws break down and the universe guards its deepest, most fundamental secrets. Black holes also teach us something profound about the very nature of the universe, that space and time are not just a fixed stage where events occur, but are instead active participants in the cosmic dance. They can be stretched, compressed, curved, and even, in a sense, broken. A black hole is the most dramatic, visible manifestation of this extraordinary flexibility of space-time. In its presence, the very dimensions of reality are distorted to the point of becoming unrecognizable. And yet, despite all their terrifying strangeness, black holes adhere to precise mathematical rules. They are neither capricious nor unpredictable. They follow Einstein's equations with astonishing exactitude. This tells us that even in the wildest extremes of the cosmos, where everything seems to be falling apart, there is still order, structure, and definite laws that we can decipher. Physics does not surrender to the extreme. Instead, it adapts, it expands, and it finds new, inventive languages to describe what once seemed utterly indescribable. Some scientists have speculated about the possibility of utilizing black holes as powerful energy sources in a far-off future. The idea involves harnessing the rotation of a black hole through a concept called the Penrose process, where energy is effectively extracted from the whirling space-time surrounding the event horizon. Others have imagined highly advanced civilizations that might live near black holes, taking advantage of the extreme time dilation to effectively travel into the future. If you could orbit very close to the event horizon for one of your personal years, centuries, or even millennia could pass in the rest of the universe. This is a form of one-way time travel into the future, explicitly permitted by the established laws of physics. But beyond the futuristic speculations, black holes hold immense scientific value here and now. They are natural laboratories where we can study gravity in its most extreme form, where we can test the predictions of general relativity to their absolute limits. Every observation of a black hole, every precise measurement of its properties, brings us one step closer to fully comprehending the fundamental laws that govern the entire universe. And perhaps, one day, those observations will finally reveal the missing link we seek between general relativity and quantum mechanics, the elusive theory of everything that physicists have been searching for over decades. So, as you sink into slumber, remember that out there, in the consuming darkness of space, exist objects so intensely dense that they curve the very fabric of reality. Places where time stops, where matter vanishes, where the rules we know simply cease to apply. Black holes are the ultimate guardians of the cosmos' deepest secrets, and every one of them is an open invitation to continue asking, to continue exploring, and to continue searching for answers in the darkest corners of the universe. Chapter 6. Dark Matter, the Invisible Skeleton of the Cosmos. Imagine that everything you can see, everything that shines in the night sky, the stars, the galaxies, the nebulas, represents barely 5% of the entire universe. The rest, the remaining 95%, is completely invisible. It reflects no light, emits no radiation, and does not interact with ordinary matter in any way that we can directly detect. And yet, it is undeniably there, holding the cosmos together like an invisible skeleton that maintains the fundamental structure of the universe. This phenomenon is dark matter, one of the most profound and persistent mysteries of modern science. The initial concept and eventual discovery of dark matter began with an uncomfortable, unexplained observation. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the motion of galaxies within the Coma cluster, a massive group of galaxies tightly bound by gravity. He meticulously measured the speed at which these galaxies were moving and calculated exactly how much visible mass would be necessary to hold them gravitationally together. The startling result was this: the galaxies were moving so rapidly that they should have dispersed and flown apart long ago, unless there was significantly more mass present than could be visually observed. Zwicky proposed that some kind of invisible material must exist, a dunkel materie, or dark matter, that provided the crucial additional gravity needed to keep the cluster intact and bound. For decades, that radical idea was largely ignored or treated with heavy skepticism. But in the 1970s, the American astronomer Vera Rubin conducted independent observations that unequivocally confirmed the rotational problem. Rubin studied the rotation curves of spiral galaxies, measuring the velocity at which stars orbit the galactic center at various distances. According to classical Newtonian laws of gravity, the stars farthest from the center should move more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin discovered something profoundly strange. The stars, located on the far edges of the galaxies, were moving just as quickly as those near the center. It was as if a massive, invisible halo of mass was extended far beyond the visible stars, providing the necessary additional gravitational force. Since those initial findings, the evidence supporting the existence of dark matter has steadily accumulated from multiple, independent directions. One of the most compelling lines of proof comes from gravitational lensing. When the light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravity of that cluster curves the path of the light, acting like a cosmic lens that distorts and amplifies the image of the faraway galaxy. By precisely measuring this distortion, astronomers can calculate how much mass the lensing object contains. And time again, these calculations consistently show that far more mass is present than we can actually see. Galaxy clusters contain anywhere from 5 to 10 times more dark matter than visible luminous matter. Another powerful piece of evidence originates from the cosmic microwave background, CMB, radiation, the pervasive remnant radiation of the Big Bang that uniformly fills the entire universe. Tiny, subtle temperature variations within the CMB reveal how matter was distributed in the early universe, barely 380,000 years after the Big Bang itself. The specific patterns we observe only make sense if we include the presence of dark matter in our theoretical models. Without it, the galaxies and the large-scale structures we see today simply would not have had sufficient time to form. Dark matter, therefore, acts as the gravitational scaffolding upon which the visible universe was ultimately built, providing the crucial extra gravity that allowed ordinary gas to condense into the stars and galaxies we observe. So, what exactly is this pervasive dark matter? The short, unsettling answer is, we do not know. We know conclusively what it is not. It is not made of ordinary atoms, baryonic matter. It does not emit light or electromagnetic radiation of any kind, and it does not interact with normal matter except through the force of gravity. That effectively rules out almost all known particles. Scientists have proposed several possibilities, the most popular being the idea that dark matter is composed of as yet undiscovered exotic particles, such as WIMPs, an acronym for Weakly Interacting Massive Particles. These hypothetical particles would possess mass, allowing them to exert gravity, but they would barely interact with ordinary matter, rendering them practically invisible and undetectable. For decades, physicists have relentlessly attempted to detect these elusive particles directly. They have constructed enormous, sensitive detectors in deep underground mines, shielded from background cosmic radiation, hoping to capture the occasional, rare collision of a dark matter particle with an ordinary atomic nucleus. To date, they have had no conclusive success. They have also tried to produce dark matter in particle accelerators, like the Large Hadron Collider, LHC, recreating the extreme energetic conditions of the early universe where these particles might have been formed. But again, they have found no definitive proof. it is an extraordinary quest, searching for a ghost that we know exists because we can clearly observe its influence, but which resolutely refuses to show itself directly. Another intriguing proposal is that dark matter might be composed of primordial black holes, small, non-evaporating black holes that would have formed in the very first instance after the Big Bang, before stars had even begun to form. These black holes would be too small to detect individually, but collectively they could provide the necessary additional mass we observe. However, recent astronomical observations have placed strict limits on this possibility, suggesting that primordial black holes, if they exist at all, cannot account for all of the missing dark matter. There is also the most radical possibility that dark matter does not exist at all, and what we truly need is to modify our laws of gravity. Certain theories, such as MOND, modified Newtonian dynamics, propose that gravity behaves differently on galactic scales than the way predicted by Newton's theory, or even Einstein's general relativity. According to these ideas, galaxies would not require dark matter to explain their strange rotation curves because gravity itself functions distinctly over vast distances. But these modified theories struggle to explain all the observations simultaneously, particularly those related to galaxy clusters and the cosmic microwave background. The truly fascinating aspect of dark matter is that while we cannot see it or physically touch it, it is virtually everywhere. It passes through the Earth constantly. Millions of dark matter particles could be streaming through your body at this very moment without you ever noticing. They do not collide with your atoms. They leave no trace. They simply pass like ghosts right through ordinary matter. The galaxy we inhabit, the Milky Way, is entirely encased in a gigantic halo of dark matter that extends far beyond the visible distribution of stars. This massive halo contains approximately 10 times more mass than all the stars, planets, and gas clouds combined. Dark matter also plays an absolutely crucial role in the formation of cosmic structures. In the early universe, shortly after the Big Bang, matter was distributed fairly uniformly with only tiny variations in density. Gravity naturally amplifies these variations. Slightly denser regions attract more matter, becoming even denser. However, ordinary matter, composed of atoms, interacts powerfully with radiation and heats up, which actively works against gravitational collapse. Dark matter, by not interacting with radiation, does not have this problem. It was able to collapse freely, forming dense clumps that acted as gravitational seeds. Subsequently, ordinary matter fell into these massive gravitational wells, eventually forming the galaxies that we observe today. In a very real sense, dark matter is the invisible architect of the cosmos. Without it, the universe would be a vastly different place, most likely too uniform for the formation of galaxies, stars, or planets. We would not be here to contemplate it. So even though we cannot see it, we owe our very existence to its pervasive presence. It serves as a humbling reminder that the universe is not primarily composed of the things we know, but rather something far more pervasive and mysterious. Scientists continue their dedicated search for definitive answers. New, more sensitive detectors are under intense development. More powerful telescopes are meticulously scrutinizing the sky for indirect signals, and theorists are exploring increasingly exotic ideas. Perhaps dark matter is composed of axions, incredibly lightweight hypothetical particles that would behave more like waves than traditional particles. Or maybe it is made up of sterile neutrinos, massive cousins of ordinary neutrinos that barely interact with anything. Or perhaps it is something else entirely. Something so fundamentally different that we have not even conceived of it yet. In the meantime, dark matter remains one of the largest and most challenging enigmas in science. It is a monumental gap in our knowledge. a sober reminder that even with all our advanced technology and mathematics, we remain profoundly ignorant about the fundamental composition of the universe. And perhaps that is the most thrilling realization of all, knowing that such enormous secrets are patiently waiting to be discovered, such deep mysteries that could completely revolutionize our understanding of reality itself. So, as you close your eyes tonight, remember that you are constantly surrounded by something invisible, something that holds the galaxies together and shapes the cosmos. Dark matter is there, silent and imperceptible, fulfilling its essential function in the grand tapestry of the universe, patiently awaiting the day when we finally unravel its true, fundamental nature. And there is something profoundly poetic about this mystery. Throughout all of human history, we have gazed at the night sky and seen light, the stars, the planets, the brilliant galaxies. We have built our entire branch of astronomy around what is visible, but now we know that the overwhelming majority of the universe does not shine. It is hidden in the darkness, invisible to both our eyes and our most powerful telescopes. It is as if we have been reading a book, paying attention only to the printed words, completely oblivious that a much larger, more significant text is written in invisible ink between the lines. The dedicated quest for dark matter also teaches us a crucial lesson about the scientific method. We do not need to observe something directly to confidently know that it exists. Sometimes, powerful, indirect evidence is perfectly sufficient. Just as we know that the wind exists because we see how it moves the leaves, even though we cannot see the air itself, we know that dark matter exists because we see how its gravity fundamentally affects the rotation of galaxies and the large-scale structure of the universe. Science is not just about direct observation, it is also about inference, about constructing elegant models that comprehensively explain what we see, even when those models necessarily include elements that we cannot immediately detect. Some scientists speculate that dark matter could form its own intricate, complex structures, entirely separate from the visible world. There could be dark galaxies made solely of dark matter, without a single shining star, floating invisibly through space. There could be dark planets orbiting in dark solar systems that we will never observe. There might even be exotic forms of physics occurring solely within the so-called dark sector, processes that have no known equivalent in the world of ordinary matter. It is essentially a parallel universe superimposed upon our own, sharing the exact same space but never fundamentally interacting with our physical reality. The final, compelling irony is that we, made of ordinary matter, atoms that shine and interact, are the extreme minority. We are the rare exception in a universe overwhelmingly dominated by the invisible. And yet, here we are, conscious, observing, and intensely questioning. Dark matter may constitute the majority of the cosmos, but it is the tiny fraction of ordinary matter that has given rise to life, to thought, and to curiosity. We are small, rare, and ephemeral. Yet we are the only beings capable of contemplating the mystery and asking what it all means. Chapter 7. Dark Energy, the Force Pushing the Universe Apart. If dark matter serves as the invisible structural skeleton of the cosmos, then dark energy is its most mysterious driving force. It accounts for approximately 70% of everything that exists in the universe, yet we have no idea what it fundamentally is. The one fact we know with absolute certainty is that it is actively pushing the universe outward, relentlessly accelerating its expansion, separating galaxies from one another at increasingly faster rates. It is as if the very vacuum of space possesses an inherent pressure, a repulsive force that successfully counters gravity on cosmic scales. And that force is winning the cosmic battle. The story of dark energy begins in the late 1990s with a discovery that sent shockwaves through the entire scientific community. Two teams of astronomers, working completely independently, were studying Type 1a supernovae, which are stellar explosions that possess a specific, highly predictable peak brightness. These supernovae function as essential standard candles in the cosmos. By knowing their intrinsic luminosity, astronomers can calculate their exact distance by measuring how bright they appear from Earth. Simultaneously, by observing the redshift of their light, scientists can determine how quickly they are moving away from us due to the universe's expansion. Scientists fully expected to find that the universe's expansion was gradually decelerating due to the collective gravitational pull of all the matter it contains. After all, if the Big Bang was the initial explosion that set everything into motion, gravity should naturally be slowing that expansion down, much like Earth's gravity slows a ball thrown upward. But what the teams discovered was the exact opposite. The most distant supernovae were consistently fainter than expected, which meant they were farther away than they should have been according to the standard models. The universe was not just expanding, it was expanding at an ever-increasing accelerated rate. It was a result so profoundly unexpected that at first many thought there had to be a significant error in the raw data or in the analysis. But both independent teams arrived at the identical conclusion using different methodologies. The evidence was irrefutable. Something unknown was forcefully driving the accelerated expansion of the universe. This unknown agent was dramatically named dark energy, a moniker that perfectly reflects our profound scientific ignorance regarding its true nature. We do not know what it is, where it comes from, or precisely how it works. We only know it is pervasive, and that it overwhelmingly dominates the total energy content of the cosmos. One of the simplest, most elegant explanations for dark energy is the cosmological constant, an idea originally proposed by Albert Einstein back in 1917. Einstein was attempting to apply his theory of general relativity to the universe as a whole, but he encountered a major problem. His equations mathematically predicted that the universe must be either expanding or contracting. It could not remain static. At the time, the prevailing belief was that the universe was eternal and immutable. So Einstein arbitrarily added a mathematical term to his equations, the cosmological constant, which represented a kind of vacuum pressure that perfectly counteracted gravity and kept the universe structurally stable. Years later, when Edwin Hubble definitively discovered that the universe was indeed expanding, Einstein famously discarded the cosmological constant, calling it his biggest blunder. But the irony is that this constant may have been correct after all, just with a different purpose. Instead of keeping the universe static, the cosmological constant could be the definitive explanation for dark energy, an intrinsic property of empty space that generates a uniform, repulsive pressure. According to this interpretation, every cubic meter of space contains a tiny, inherent amount of energy, and as the universe expands and creates more space, more dark energy is effectively generated, accelerating the expansion even further. However, there are significant problems with this particular explanation. When physicists attempt to calculate how much energy the quantum vacuum should possess based on the principles of quantum mechanics, they arrive at an astronomically large number, approximately $10 to $120 times greater than the observed value of dark energy. This is a discrepancy so colossal that it is famously known as the worst fine-tuning problem in the history of physics. Something is fundamentally wrong, either with our theoretical calculations, with our current understanding of the quantum vacuum, or with the idea of the cosmological constant itself. Another leading possibility is that dark energy is not a fixed, constant property of space, but rather a dynamic field that varies over time and location, similar in principle to the Higgs field that imparts mass to particles. Some physicists have proposed the existence of a theoretical field called quintessence, whose intensity could change throughout the history of the cosmos. If this dynamic model is true, dark energy would not be constant. Instead, it would have been weaker in the distant past and could become either stronger or weaker in the future, dramatically altering the ultimate fate of the universe. The implications of dark energy for the cosmos's future are profound, and in a sense, quite melancholic. If the accelerated expansion continues indefinitely, the universe will become progressively colder, emptier, and darker. Distant galaxies are already receding from us at velocities that effectively exceed the speed of light, not because they are physically moving that fast, but because the space itself between us and them is expanding. Eventually, those faraway galaxies will cross the cosmological horizon and disappear from our view forever. The light they emit will never reach us, because space expands faster than light can travel. Within hundreds of billions of years, all the galaxies outside of our local group, the small gravitationally bound cluster that includes the Milky Way, Andromeda, and a few smaller dwarf galaxies, will have vanished beyond the observable horizon. Astronomers of the far future, should they exist, will observe a universe vastly different from our own. Just a few nearby galaxies floating in an infinite, dark void. They will have no way of knowing that there were ever billions of other galaxies. The observable universe will have shrunk to an ever-diminishing bubble of light in a boundless ocean of darkness. And if dark energy continues to strengthen its dominion, it could lead to an even more extreme scenario known as the Big Rip. In this cataclysmic outcome, the acceleration of expansion becomes so incredibly intense that it not only tears galaxies apart, but eventually rips apart the galaxies themselves, then the star systems, then the planets, then the atoms, and finally, even the subatomic particles. The universe would literally be shredded down to its last fundamental component. However, this worst-case scenario would only occur if dark energy's strength increases over time, a dynamic behavior that we do not yet know to be true. Another possibility is the Big Freeze, or the Great Cooling, where the expansion continues forever, but at a rate that does not dramatically increase. In this scenario, the universe simply becomes increasingly diluted and cold. Stars exhaust their fuel and flicker out one by one. Black holes consume any remaining matter and then slowly evaporate through Hawking radiation. Eventually, all that remains is a near-perfect vacuum at temperatures barely above absolute zero, a dark, silent, eternal cosmos where nothing ever changes again. But the understanding of dark energy is not all pessimism. It also teaches us something fundamental about the nature of the universe, that the vacuum is not empty. Space itself, even when it contains no matter or radiation, possesses properties, structure, and energy. It is an active field, not a passive backdrop. And that crucial realization has profoundly changed our understanding of modern physics. The quantum vacuum is filled with virtual particles constantly popping in and out of existence, fluctuations that leave measurable imprints in laboratory experiments. Dark energy could ultimately be a manifestation of these quantum fluctuations on a massive, cosmic scale. Scientists continue to study dark energy with increasingly precise observations. Space missions like the European Space Agency's Euclid satellite and NASA's upcoming Nancy Grace Roman Space Telescope are specifically designed to map the distribution of dark matter and measure the universe's expansion with unprecedented accuracy. Every new measurement brings us one step closer to comprehending exactly what this mysterious force is that fundamentally dominates the destiny of the cosmos. In the meantime, dark energy remains one of the largest and most compelling enigmas in modern science. It is a powerful reminder that the universe is far stranger than we ever imagined. For centuries, we believed that gravity was the dominant force on cosmic scales, the force that pulls everything inward. But now we know that there is another force, one that forcefully pushes outward, and one that is currently winning the cosmic battle. And this force is made of something we cannot see, cannot touch, and can barely even begin to comprehend. So as you sink deeper into your rest, consider this incredible fact. The universe surrounding you is actively expanding, stretching, and separating. With every second that passes, the space between galaxies grows slightly wider. Dark energy is silently, implacably at work, pushing the cosmos toward a final future we cannot yet fully imagine. It is an invisible, repulsive force that dictates the destiny of everything that exists, a profound mystery that floats in every corner of the vacuum, patiently waiting for the day we finally decipher its ultimate secret. And there is something deeply unsettling in the idea that the universe is not merely expanding, but actively accelerating. It is as if the cosmos is in a hurry to reach its end, eager to tear apart everything that was once cosmically bound. Dark energy does not respect large-scale gravitational ties. It does not care that galaxies took billions of years to form, or that cosmic structures are the result of delicate, complex processes. It simply pushes, relentless and eternal, driving everything toward the final dispersion. But perhaps there is a peculiar beauty in that transience. The universe we currently know, with its brilliant galaxies and sparkling, distinct stars, is not a permanent state. It is a fleeting moment in a much longer cosmic history. We are living in a special epoch, a window of time where the universe is dense enough for complex structures to exist, yet not so dense as to collapse under its own gravity. It is the precise time for life, consciousness, and curiosity to emerge. And dark energy reminds us that this opportune moment will not last forever. Philosophers and physicists sometimes discuss the fine-tuning problem, the observation that the fundamental constants of the universe appear to be calibrated with extraordinary precision to allow for the existence of life. If dark energy were just slightly stronger, the universe would have expanded so rapidly that galaxies never would have had the chance to form. If it were slightly weaker, the universe might have collapsed back in on itself before life could arise. We are here in part because dark energy has the precise intensity it does. Is this a mere coincidence, or is there something much deeper at play? No one knows the definite answer, but the profound question remains wide open, provocative, and insistent. Chapter 8: Quasars, Pulsars, and Gravitational Waves. Up until now, we have explored strange objects and invisible forces, but the universe also gifts us with powerful phenomena that we can directly detect. Signals that travel across the cosmos, carrying information about cataclysmic events that occurred billions of years ago. Among these cosmic messengers, 3 stand out for their ability to reveal the deepest secrets of the universe. Quasars, brilliant beacons fueled by supermassive black holes; pulsars, cosmic clocks of extraordinary precision; and gravitational waves, ripples in the very fabric of space-time that allow us to listen to the universe in a completely new and revolutionary way. Let's begin with quasars, an abbreviation for quasi-stellar radio sources. When they were first discovered in the 1960s, astronomers had no idea what they were. They looked like ordinary stars in optical images, yet they emitted colossal, unexplained amounts of energy across all wavelengths: radio, infrared, visible light, and X-rays. Some quasars are so intensely bright that they far surpass the luminosity of entire galaxies, despite the fact that all that energy originates from a region smaller than our own solar system. It was as if scientists had found a cosmic lighthouse capable of illuminating the entire universe from its most remote, distant corner. The explanation eventually arrived when scientists realized that quasars are, in fact, active galactic nuclei, AGN, galaxies whose centers contain a supermassive black hole that is actively devouring surrounding matter at a frantic pace. As gas, dust, and even entire stars spiral toward the black hole, they form rapidly spinning accretion disks, where the matter is heated to millions of degrees due to intense friction. This superheated matter emits powerful, fierce radiation just before it crosses the event horizon and disappears forever. Some of the material does not fall directly in, but is instead violently ejected in relativistic jets, streams of particles accelerated to near the speed of light that shoot out from the black hole's poles, extending for millions of light years. Quasars were far more common in the early universe, billions of years ago, when galaxies were younger and possessed much more readily available gas to feed their central black holes. Observing a distant quasar is literally like looking backward in time, viewing the universe when it was a much more chaotic and violent place. Some quasars are so incredibly far away that their light has traveled for over 10 billion years to reach us, meaning we are seeing them as they were when the universe was barely a tenth of its current age. These energetic objects also help us understand how galaxies evolved. Today, we know that almost all large galaxies host a supermassive black hole at their center, but most of these are currently dormant or only slowly accreting matter. Quasars show us what those galaxies were like during their energetic youth, when their black holes were rapidly growing, consuming everything in their path. The enormous energy liberated by these active black holes was so intense that it likely influenced star formation throughout the entire galaxy, effectively regulating galactic growth and shaping the large-scale structure of the universe we see today. Next, let's revisit pulsars, which we briefly mentioned when discussing neutron stars. Pulsars are rapidly rotating neutron stars that emit focused, narrow beams of radiation from their magnetic poles. Because these beams spin along with the star, we detect them as regular, precise pulses every time the beam sweeps past and points toward Earth, like the rotating light of a lighthouse on the coast. Some pulsars spin hundreds of times per second, meaning they complete a full rotation in just a few milliseconds. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning so quickly that its equatorial surface moves at a significant fraction of the speed of light. The sheer regularity of pulsars is astonishing. Some are so precise that they rival the best atomic clocks we have on Earth. This inherent precision makes them extraordinary scientific tools. Astronomers utilize pulsars to meticulously study the distribution of matter within the galaxy, to measure vast cosmic distances with great accuracy, and to test the predictions of general relativity under extreme high-gravity conditions. They have also been seriously proposed as potential navigation systems for future deep space spacecraft, a kind of cosmic GPS based on the highly predictable time of arrival of pulses from multiple known pulsars. But there is an even more fascinating aspect: pulsars in binary systems. When two pulsars orbit each other, or when a pulsar orbits another neutron star or a black hole, the entire system actively loses orbital energy by emitting gravitational waves. This precise energy loss causes the orbits to gradually shrink, and the two objects spiral closer together in a motion that will eventually terminate in a catastrophic collision. It was by observing a binary pulsar system, famously known as PSR B1913 plus 16, the Hulse-Taylor binary, that astronomers obtained the first indirect evidence of the existence of gravitational waves, decades before they were ever directly detected. And this brings us to the third cosmic messenger, gravitational waves. Albert Einstein first predicted their existence in 1916 as an inevitable consequence of his theory of general relativity. According to Einstein, massive accelerating objects curve spacetime around them, and when these objects are violently accelerated, especially in cataclysmic events like the merger of black holes or neutron stars, they generate ripples in the fabric of spacetime that travel outward at the speed of light, carrying information about the event that created them. However, detecting gravitational waves is extraordinarily difficult. Even the waves generated by the most cataclysmic events, such as the merger of two black holes, are incredibly minute and weak by the time they reach Earth. They stretch and compress space by tiny amounts, far smaller than the diameter of a single proton. For decades, scientists attempted to construct detectors sensitive enough to capture these elusive signals, but they failed repeatedly until, in September 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, detectors in the United States finally succeeded. The detected signal originated from two black holes, each approximately 30 times the mass of the Sun, which had been orbiting each other for billions of years, gradually spiraling inward in a death embrace. In the final fraction of a second before they merged, they were spinning around each other hundreds of times per second, moving at velocities close to half the speed of light. When they finally collided, they released more energy in the form of gravitational waves than all the light emitted by all the stars in the observable universe combined in that same instant. It was an event so violent that it physically shook the fabric of space-time, and those ripples traveled 1,300,000,000 years across the cosmos before reaching Earth, where the LIGO detectors registered them. That landmark discovery opened a completely new and profound window onto the universe. Throughout the entire history of astronomy, we have observed the cosmos using light in its various forms: visible, infrared, ultraviolet, X-rays, and radio waves. But gravitational waves are fundamentally different. They are not electromagnetic radiation, they are actual distortions of space-time itself. They allow us to actively listen to events that are entirely invisible to ordinary telescopes, such as the mergers of black holes, which emit absolutely no light. It is as if humanity had been deaf throughout its entire history and suddenly acquired the sense of hearing, revealing a universe filled with dynamic sounds that we had never before perceived. Since that initial detection, gravitational wave observatories have recorded dozens of mergers of black holes and also of neutron stars. One of the most thrilling detections occurred in August 2017, when LIGO and its European counterpart Virgo detected gravitational waves stemming from the collision of two neutron stars. Unlike black hole mergers, which are completely dark, this collision also produced light. Telescopes worldwide immediately focused on the source, observing a brilliant explosion known as a kilonova, where massive quantities of heavy elements like gold, platinum, and uranium were forged. It was the very first time astronomers could study the same event using both gravitational waves and light, marking the birth of multi-messenger astronomy. Gravitational waves are also teaching us new facts about black holes. For example, we have discovered that merging black holes can possess masses greater than what some theoretical models had previously predicted. We have also learned that mergers do not always occur between objects of similar mass. Sometimes, a much larger black hole effectively devours a much smaller one. and every new detection refines our comprehension of how space-time behaves under the most extreme conditions, confirming time and again that Einstein's predictions were correct with astonishing accuracy. But gravitational waves also pose new questions. Do sources of gravitational waves exist that we have yet to detect? Could we capture waves originating from the Big Bang itself, carrying information about the first tiny fractions of a second of the universe? Are there exotic events such as the evaporation of primordial black holes or collisions of cosmic strings that might generate detectable signals? Scientists are working diligently on increasingly sensitive detectors, both in space and on Earth, with the urgent hope of answering these profound questions. Quasars, pulsars, and gravitational waves share an underlying commonality. They are all messengers that bring us news of the most violent and extreme events occurring in the universe. Quasars show us what galaxies were like when the cosmos was young and fierce. Pulsars give us stable cosmic clocks that allow us to study physics under conditions impossible to recreate in any laboratory. And gravitational waves allow us to directly feel the vibrations of space-time, listening to the universe in a way we never could have previously imagined. So as you relax and your mind quiets, consider this incredible thought. Right now, gravitational waves from events that occurred millions or billions of years ago are passing right through you, stretching and compressing your body by imperceptible amounts. Pulsars are sending out precise pulses of light that cross the galaxy with an accuracy that surpasses our best clocks. And distant quasars are blazing with the fury of entire galaxies, fueled by black holes that devour suns as if they were grains of sand. The universe is vividly alive with signals, and we are only just beginning to truly hear them. Chapter 9. Interstellar Objects and Cosmic Visitors. For thousands of years, humans have gazed up at the night sky, believing that the solar system was a completely closed system, a small, isolated cosmic island separated from the rest of the universe. The planets orbited the sun, the comets and asteroids wandered among them, but everything was thought to remain safely within our gravitational bubble. It never occurred to us that objects from other star systems could actively visit us, traverse our cosmic neighborhood, and continue their journey into the surrounding darkness. But in October 2017, that notion was shattered when astronomers detected the first confirmed interstellar visitor, a mysterious object they named Oumuamua, a Hawaiian word meaning scout or messenger arriving first from afar. Oumuamua was discovered by the Pan-STARRS telescope in Hawaii while it was hurtling through the inner solar system at a breathtaking speed. Its trajectory was unmistakable, an open hyperbola that could not possibly be the result of a bound orbit around the sun. It was undeniably coming from the outside, from somewhere among the distant stars, and after passing close to the sun, it would continue its journey out into interstellar space, never to return. It was a fleeting visitor, a cosmic vagabond that had been traveling through the galaxy for millions of years before briefly intersecting with our tiny corner of space. What made Oumuamua even more deeply intriguing was its unusual shape and perplexing behavior. Initial observations strongly suggested that it was extremely elongated, with a length-to-width ratio of approximately 10:1, giving it the appearance of a gigantic cigar, or perhaps a flattened disk viewed edge-on. No asteroid or comet in our own solar system possesses such an extreme, unusual shape. Furthermore, it showed no signs of typical cometary activity. It lacked a discernible tail of gas or dust, despite having passed close to the sun, where the heat should have easily evaporated any ices on its surface. It appeared to be made of solid rock, or some other, more exotic, robust material. But then, something truly bizarre happened. As Oumuamua moved away from the Sun, astronomers noticed that it was accelerating slightly, more than could be explained by the Sun's gravity alone. Normally, comets exhibit this kind of non-gravitational acceleration because gas evaporating from their surface acts like a small rocket motor, gently pushing them forward. But Oumuamua had no visible tail. It emitted no detectable gas. So, what exactly was propelling it? The number of explanations multiplied rapidly. Some scientists suggested it could be made of pure nitrogen ice, a material that evaporates without leaving any visible trace or dust. Others proposed it might be a fragment of a destroyed planet with an unusual composition that gave it unique properties. And then there was the most provocative hypothesis of all, put forward by astrophysicist Avi Loeb of Harvard University, that Oumuamua could potentially be a solar sail, an artificial structure crafted by an extraterrestrial civilization to navigate between the stars by utilizing the subtle pressure of starlight. According to Loeb, the object's highly elongated shape and its inexplicable acceleration were entirely consistent with a thin sheet of reflective material being propelled by solar radiation. The notion that Oumuamua might be alien technology was met with significant skepticism from the majority of the scientific community. The general consensus remains that it is likely a natural object with highly unusual properties, perhaps something we had simply never seen before because we had never previously detected an interstellar visitor. But Loeb's hypothesis cannot be completely ruled out based on the currently available data, and that fact alone is deeply fascinating. The mere necessity of having to seriously consider the possibility, however remote, that an interstellar object could be artificial serves as a powerful reminder of how much we still do not fully comprehend about the universe. Unfortunately, Oumuamua sped away too quickly for us to study it in necessary detail. Within a matter of months, it became too faint to be observed even with the most powerful telescopes. It is now once again deep in interstellar space, continuing its eternal journey across the galaxy, and we will probably never know with absolute certainty what it truly was. But its brief visit taught us a vital lesson. Interstellar space is not empty. It is filled with these rogue objects, fragments violently ejected from distant planetary systems that travel for millions or billions of years until they occasionally happen to cross paths with another star and its planets. In August 2019, barely 2 years after the Oumuamua discovery, a second interstellar visitor was detected. This time, it was more easily classified. It was a comet named 2I Borisov, discovered by Russian amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov behaved exactly like an ordinary comet. It possessed a bright tail of gas and dust, and its chemical composition appeared similar to that of the comets within our own solar system. Crucially, however, its orbit was clearly interstellar, confirming that it originated from an entirely different star system. The discovery of Borisov was reassuring in a certain sense. It demonstrated that interstellar objects are not necessarily bizarre or exotic. Some of them are simply ordinary comets that were violently ejected from their parent planetary systems during chaotic gravitational encounters, condemned to wander the galaxy for eons. But it also raised a host of new questions. How many of these cosmic visitors cross our solar system undetected? What information can they teach us about the complex formation processes of planetary systems around other stars? Astronomers estimate that, at any given moment, there could be several interstellar objects traversing the inner solar system, but most are simply too small or too faint to be successfully detected. With more advanced next-generation telescopes, such as the future Vera C. Rubin Observatory, which will soon begin operations, we fully expect to discover many more. Some of these may prove to be as strange as Oumuamua, or perhaps even stranger. And with every new discovery, we will learn more about the sheer diversity of objects that populate the vast gulf of space between the stars. But interstellar objects are not the only cosmic visitors that capture our imagination. There are also the rogue exoplanets, massive worlds that were ejected from their solar systems and now wander the galaxy without a parent star. These orphan planets drift through the darkness of interstellar space, frozen and solitary, with no sunlight to warm them. It is estimated that there could be billions of them in the Milky Way, potentially outnumbering the stars themselves. They were violently expelled during the chaotic early stages of planetary formation, when close gravitational encounters with other planets or with passing stars launched them out of their stable orbits. Some of these rogue planets might even retain moons, small, icy satellites that accompany them on their eternal journey. And if these planets are sufficiently massive, they could retain enough internal heat generated by radioactive decay or by tidal forces, allowing for liquid oceans to exist beneath their frozen surfaces. In theory, these subterranean oceans could potentially harbor life, organisms adapted to living in complete darkness, feeding on chemical energy rather than solar light. These would be isolated ecosystems, completely cut off from the rest of the universe, small bubbles of life floating alone in the infinite void. And then there are the truly exotic objects that scientists have proposed but have yet to observe. For instance, boson stars, hypothetical objects made entirely of bosonic particles trapped in a coherent quantum state, or the aforementioned carbon planets, worlds where the chemistry is dominated by carbon instead of silicates and oxides, creating alien landscapes of graphite and diamond under atmospheres rich in methane. Or even substellar objects, known as brown dwarfs, which are too small to be true stars, but too large to be classified as planets, glowing only faintly with the residual heat from their formation. Every one of these objects, whether they are transient interstellar visitors, lonely rogue planets, or exotic curiosities, serves as a powerful reminder that the universe is a vast and intensely dynamic place. Nothing is truly isolated or permanently separated. Star systems are constantly exchanging material, violently ejecting comets, asteroids, and even planets out into intergalactic space, where they travel for millions of years until some, by sheer chance, pass close to another star. It is a continuous cosmic exchange that has been occurring throughout the entire history of the galaxy. And this raises one final, fascinating question. Could interstellar objects potentially transport life from one star system to another? This concept is called panspermia, the hypothesis that life might spread throughout the galaxy by traveling inside comets, asteroids, or fragments of planets. If a habitable planet were struck by a large enough asteroid, the impact could launch rocky debris into space, some of which might contain trapped microorganisms deep inside. Those rocks would then travel for millions of years through interstellar space, and if one of them were to eventually crash onto another habitable planet, it could potentially seed life there. We already know that some terrestrial microorganisms are capable of surviving in the harsh environment of space for extended periods. Experiments conducted on the International Space Station have demonstrated that certain bacteria and spores can withstand the vacuum, the intense radiation, and the extreme temperatures for years. If they were protected inside a piece of rock, they could potentially survive much, much longer. It is conceivable, though highly speculative, that life on Earth has interstellar origins, that our microbial ancestors arrived here billions of years ago aboard a comet or asteroid originating from another star system. Of course, we currently have no direct evidence that this has actually occurred, and most scientists believe that life on Earth originated right here. But the possibility cannot be entirely dismissed, and it is a poignant reminder that we are intrinsically connected to the cosmos in ways we are only just beginning to grasp. The very atoms in our bodies were forged in the hearts of long-dead stars billions of years ago. The water in our oceans may have arrived aboard comets that bombarded the early Earth, and perhaps, just perhaps, the spark of life itself also came from the stars. So as you prepare to rest, consider this final image. At this very moment, somewhere in the deep space between the stars, objects are traveling silently through the darkness. Some are ancient rocks, fragments of shattered worlds that no longer exist. Others might be entire planets, frozen, homeless worlds. And maybe, just maybe, one of them is something we have never before imagined. Something that will radically change our understanding of the universe when we finally discover it. The cosmic visitors keep coming, and each one carries with it a mystery waiting to be solved. Chapter 10: Extreme Theories, Cosmic Strings, Quantum Black Holes, and Multiverses. We have journeyed through some of the most bizarre and extreme objects in the observable universe: stars made of matter compressed to the absolute limit, planets that aggressively defy our imagination, and invisible forces that fundamentally mold the cosmos. But now, in this final segment of our nocturnal voyage, we will venture into even more speculative territories, where established, known physics meets the most audacious scientific imagination. Here, on the far frontiers of human knowledge, dwell ideas that sound like pure science fiction, but are, in fact, rigorously supported by complex mathematical equations: cosmic strings, quantum black holes, and the elusive multiverse. Let's begin with cosmic strings, hypothetical objects that, if they exist, would be profound relics of the very early universe. According to certain high-level theories, immediately following the Big Bang, space-time may have stretched and cooled so rapidly that small, persistent imperfections remained in its fundamental structure, like permanent creases or wrinkles in a newly woven cosmic fabric. These wrinkles would be the cosmic strings, incredibly thin, immensely dense filaments that span enormous distances. Their thickness would be far less than that of a single atom, yet a single kilometer of cosmic string could theoretically weigh more than an entire planet. These strings, if real, would be literal fossils from the birth of the universe. They are not made of conventional matter, but of the space-time fabric itself compressed to an unimaginable limit. They would exert powerful gravity around them, severely distorting light and time, acting like an invisible cosmic blade slicing through the cosmos. If one were to pass close to Earth, it would dramatically bend space in its wake, creating a kind of gravitational mirror that would duplicate the image of the sky. We would observe the same stars and galaxies twice, one on each side of the string, as if the universe were reflected in an unseen pane of glass. No cosmic string has been definitively detected to date, but astronomers have diligently searched for their subtle signatures in the patterns of the cosmic microwave background and in the gravitational lenses that deform the light from distant galaxies. So far, nothing conclusive has been found. And yet, their possibility remains firmly on the table because the underlying equations do not prohibit their existence. They are a natural prediction of certain models within quantum field theory and the influential string theory, a radical proposal that attempts to unify all the fundamental forces of the universe into a single, cohesive mathematical description. String theory posits that at its most fundamental level, the universe is not made of zero-dimensional point particles, but of tiny, vibrating strings, one-dimensional objects far smaller than an atom. Every type of particle, every electron, every quark, every photon would be nothing more than a specific string vibrating in a different mode, like the notes plucked on a cosmic guitar. Cosmic strings would be, in a way, the scaffolding of that universal model, enduring filaments of energy that vibrate, potentially connecting distant regions of space-time. If they are real, the universe would not simply be a random collection of dispersed galaxies, but a living, resonant network where every vibration, every frequency, generates the matter and energy that we perceive. On the conceptual opposite extreme from the strings, where space is strained to the point of breaking, appear the quantum black holes. Until now, the black holes we know are described using general relativity, which perfectly explains gravity on large cosmological scales. But at their center, where density becomes infinite, classical physics fundamentally breaks down. That is the undisputed domain of the quantum, where particles obey statistical and probabilistic laws. A quantum black hole would be the attempt to successfully reconcile both worlds, Einstein's massive gravity and Heisenberg's quantum uncertainty. According to some theoretical models, the singularity that we currently imagine, that infinitely dense point at the heart of a black hole, might not exist as we describe it. Instead, there would be an extremely small but finite region, perpetually held up by powerful quantum effects that prevent total collapse. In this scenario, the black hole could potentially store and release information in ways we do not yet fully comprehend, thereby resolving the famous information paradox we discussed previously. Some physicists propose that the surface of the black hole, the event horizon, might act as a holographic membrane, a two-dimensional layer that perfectly encodes everything that falls inside in the form of complex quantum patterns. Thus, what we perceive as a perfectly black sphere would not be a mere void, but a surface of highly compressed data, a cosmic library that holds the entire record of everything that ever fell into it. This is a radical idea that would change our understanding of information, entropy, and the very nature of reality. If the event horizon is truly holographic, then perhaps the entire universe is an immense projection, a three-dimensional shadow of information stored on a two-dimensional surface at the very edge of the cosmos. It is an idea that borders on the mystical, yet it is supported by rigorous mathematics and has inspired decades of cutting-edge theoretical physics research. Other extreme theories suggest that black holes might not represent the final end of matter, but a transition. When a black hole slowly evaporates through Hawking radiation, it might reach a point where the extreme density effectively reverses and the remaining energy violently explodes outward, giving rise to a new region of space-time. In this startling view, every black hole could be the germination point of a new universe, a miniature Big Bang that creates a region of space-time disconnected from the original universe. From that powerful idea emerges one of the most provocative hypotheses in modern cosmology, the multiverse. If every collapsing black hole generates a new, disconnected space-time region, then the cosmos would be like a perpetual tree bearing infinite fruit. Each baby universe would possess its own unique set of physical laws, its own space, and its own time. Some might expand just like ours, others might collapse in mere seconds. Some would possess stars and galaxies, others might be dark voids completely devoid of structure. Each would be a natural experiment with slightly different parameters, exploring all the diverse possibilities permitted by the overarching laws of physics. This ultimate vision radically changes the concept of totality. Our universe would cease to be the whole and would instead become just one part within an infinite family of realities, each with its own history. What we call the beginning of time, the Big Bang, could have been simply the final moment of another, previous universe that collapsed into a black hole. Time would not have an absolute starting point, but would be cyclical or branching, a complex network of universes continuously being born from one another in an eternal cascade. Some mathematical models strongly support this possibility. Cosmic inflation, the phase of extremely rapid expansion that followed the Big Bang, could have occurred simultaneously in multiple regions of space, generating bubbles that evolved as independent universes. These bubbles could coexist in a metaspace that never stops inflating, giving rise to an inflationary multiverse, a panorama in which every region of the vacuum is continuously spawning new realities. For now, there is no direct empirical way to test this idea, but the equations of quantum field theory allow for its existence without any contradictions. In fact, some cosmologists argue that denying the possibility of multiple universes would be as arbitrary as having once denied the existence of other planets beyond the Earth. The core argument is simple. If the laws of physics allow something to occur, it has probably occurred somewhere at some time. And if the laws permit the creation of universes, then we should logically expect many, perhaps an infinite number, to exist. The multiverse also offers a possible explanation for the fine-tuning problem that we addressed earlier. If there exists an infinite number of universes with widely varying physical constants, then it is not surprising that at least one of them has the exact necessary conditions for the emergence of life. We are here not because our universe is uniquely special, but because only universes with the right specific conditions can produce observers who then wonder why things are the way they are. This is a form of the anthropic principle applied on a multiversal scale. We observe this universe because it is the type of universe where observers can exist. But these theoretical ideas also raise profound philosophical questions. If infinite universes exist, does it still make sense to talk about probabilities? If everything that can happen does happen in some universe, what truly distinguishes factual reality from mere fiction? And if we can never directly observe these other universes, are they truly science or just compelling mathematical speculation? These questions have no easy answers, and they significantly divide the scientific community. Some physicists believe the multiverse is the inevitable conclusion of our best theories. Others think it is an unfalsifiable idea that lies outside the proper boundaries of empirical science. At this rarefied level of scientific thought, the line separating physics from philosophy becomes incredibly thin. Many of these ideas are not yet demonstrable and may never be, but they fulfill an essential function, expanding the limits of the scientific imagination. Every one of them, from cosmic strings to baby universes, is born from the unwavering human attempt to extend the map of the possible, to explore beyond the simple boundary of the known data. Science does not advance solely through observation. It also advances through imagination. Einstein, before formulating relativity, famously imagined what the world would look like if he could ride on a beam of light. Quantum mechanics was born from thoughts that seemed absurd. Particles existing in two places at once, cats that are simultaneously alive and dead until they are observed. Each of those groundbreaking ideas seemed like sheer fantasy until meticulous experiments confirmed that, in some fundamental way, reality is truly that strange. Therefore, in the realm of the theoretical, imagination is not the opposite of science. It is its natural extension. It allows for the creation of hypotheses that time and technology will eventually put to the test. And while many will eventually fall into obscurity, some will survive, permanently changing our understanding of the universe. Perhaps the limit of the comprehensible is not a fixed barrier, but a moving horizon. As we reach it, it recedes just a little bit further. Every time we believe we have reached the end of knowledge, a new question shows us that we were only just beginning. After traversing galaxies, black holes, invisible matter, and hypothetical multiverses, the only thing that remains perfectly clear is our smallness. The universe does not fit within our definitions, nor even within our most advanced mathematics. Every answer opens up 10 new questions, and every discovery reveals how much we still ignore. In the end, that is the true, profound lesson of science, not to master reality, but to learn to coexist with the mystery. Because knowledge does not eliminate the unknown, it simply enlarges it, illuminates it, and makes it visible. And perhaps its ultimate beauty lies right there, in showing us that even the infinite possesses boundaries, though those boundaries are constructed entirely of pure curiosity. We have explored a universe filled with strangeness, from the densest stars to the invisible forces that both sustain and tear it apart. We saw matter that does not shine, energy that propels the vacuum, impossible worlds, and theories that push the boundaries of human thought. And we have understood that the universe is not strange because it is chaotic, but because we do not yet fully comprehend its language. Thank you for sharing this nocturnal journey into the enigmatic. If you enjoyed the experience, please leave your like and join Deep Space Calm to continue delving into the universe's many secrets. May you have a good night. May your rest occur under a sky filled with enigmas, where every single flicker of light is a profound singularity that reminds us how much there is still left to uncover.